to the explainer. So, how do you actually measure a piece of software? I mean, is it just the number of lines? The file size? Today, we're going to crack the code on a scientific method for measuring software itself, a technique that's over 40 years old but is still, you might be surprised, pretty relevant.
So here's the plan for today. First, we'll get into why we even need a different way to measure code. Then, we'll break down the basic building blocks Halstead came up with, dive right into his core metrics, and then see how they all work with a real-world code example. And finally, we're going to weigh the pros and cons to see how this old idea really holds up today.
Okay, so first things first, let's set the stage. Why did we need a new way to measure software to begin with? Well, it all boils down to the problem with the most obvious metric there is, just counting the lines of code.
I mean, think about it for a second. Is a 100-line program that just prints some text 100 times really as complex as a single super dense line of a mathematical algorithm? No way. Counting lines tells you about the length, sure, but it tells you almost nothing about the complexity, the difficulty, or the sheer mental effort it takes to understand it. We clearly need a better way to measure this stuff.
And that is exactly where Maurice Halstead came in. Way back in 1977, he had this really fundamental insight. He suggested that instead of looking at lines, we should think of a program as just a collection of its smallest parts, which he called tokens. And that one seemingly simple shift in perspective, it's the key to this whole system.
Okay, so if a program is just a collection of tokens, what exactly are these things? Well, Halstead boiled everything down to just two fundamental categories.
Halstead's big idea was just brilliantly simple. He basically said that any piece of code in any language is just made up of two things: operators, which are the actions, the verbs of the code, and operands, which are the variables and values being acted on, the nouns. Seriously, that's it. So once you see code this way, you can start counting, and Halstead's entire system, I mean all of it, is built on these four simple measurements you see here. How many unique or distinct operators and operands you have, that's N1 and N2, and then the total number of times you use them, that's N1 and N2. Everything else is going to flow from these four numbers.
And this is where it gets really powerful, because by combining these four super simple counts in different ways, we can get some surprisingly deep insights into the software we're looking at.
First up, we've got program volume. Now, this has nothing to do with the file size on your computer. As you can see from the formula, it's calculated from our token counts to measure the amount of information the program actually contains. You can think of it as the size of the idea being coded. A higher volume means there's just more for a developer to mentally juggle. Yeah, this really nails it. It's not about how many pages of code you have. It's about how much space it takes up in your head when you're trying to figure it out. A program can be super short but have a crazy high volume if it's using a ton of different operators and operands in a really dense way. Next, we have difficulty. This metric basically tries to put a number on how tricky a program is to work with. For instance, if your code reuses the same few variables over and over again for different things, well, your difficulty score is going to go up. It's a sign that a developer has to keep track of more context for each variable, which makes the code way more prone to bugs.
So you take the size of the idea, that's the volume, and you multiply it by how hard it is to work with, that's the difficulty, and what you get is programming effort. It's basically a single number that tries to capture all the brainpower it took to bring that piece of software to life.
And this part is just wild. To turn that abstract idea of effort into actual time, Halstead used the work of a psychologist, John Stroud. Stroud figured out that the human brain can make somewhere between 5 and 20 elementary decisions per second. Halstead just picked 18 as his standard, a value we now call the Stroud number.
All right, that's a whole lot of theory, so let's make this real. Let's see how this actually works with a real piece of code.
Okay, so what we're going to look at is this pretty simple C function. All it does is take an array of numbers and sort them. It's a classic programming problem, right? Which makes it the perfect thing for us to analyze here. So first step, we got to break the code down and just count everything. And you can see it right here in the table. We found 14 distinct operators, things like if and for, and 10 distinct operands, which are our variables. Then we counted every single time they appeared, and that gives us our four key numbers for the formulas, N1, N2, N1, and N2. Okay, now for the fun part. We plug those numbers into our formulas. First result, the program volume. For this little sorting function, it comes out to just over 417 bits. That is the size of the idea we're working with here.
Next, we calculate the difficulty, which clocks in at about 37. Now, by itself, a number like 37 doesn't mean a whole lot. But, and this is the key, we can now compare it to another sorting algorithm and have a real quantitative way to say which one is simpler or maybe less likely to have bugs.
And finally, the grand finale. We take the volume, we multiply by the difficulty to get the effort, and then we divide by that Stroud number, 18, and the results? The model predicts it would take a focused programmer about 610 seconds. That's just over 10 minutes to write this exact function from scratch. Pretty neat, huh?
Okay, so this all leads to the big question, right? Is any of this actually useful in the real world? I mean, it's a cool theoretical exercise, but what are the pros and cons of actually using these metrics today?
Well, the trade-off is pretty clear. On the plus side, you can totally automate this stuff. It works in any programming language, and it gives you a hard number for code quality. They could even help predict where bugs might pop up. But on the other hand, it's got some massive blind spots. I mean, it tells you nothing about the user interface or how the whole system is designed. And its accuracy, well, it really hinges on some big assumptions about how people write code.
All right, let's zoom out and wrap this up. After all of this, what's the one big takeaway you should remember about Halstead's metrics? At the end of the day, what Halstead really gave us was a whole new way to think. He gave us the first real tools to measure something as kind of squishy as software complexity with actual numbers. He got us to stop just counting lines of code and forced us to look deeper, at the code's actual internal structure. And that brings us to a really interesting question for the future. You see, Halstead designed all of this to measure code written by people. But now we've got AI writing more and more of our code. So does a measure of human mental effort even make sense?